And now please welcome back to the stage, Dr. Deb Palmer.
Hello again. Tom Cager, the program manager for the domain-specific system-on-chip program, was unable to attend today, so I will present today's first demo. Today's extreme level of integration allows us to implement complete systems on a single chip. Integrated circuits are no longer just a CPU or some memory or a specialized accelerator, but are now capable of incorporating all of these parts and more onto a single system on chip, or SoC. And they're everywhere. They're the engines running your fitness tracker and your cell phone. They're controllers for autonomous vehicles, and there are many more SoC applications across the commercial and defense world. SoCs generally are created and optimized for a specific application domain where they're called upon to execute a family of applications relevant to the target domains like autonomous vehicles, communications, or bioinformatics. For example, the autonomous vehicle domain application set includes radar, LiDAR, video, image processing and recognition, voice control, steering, braking, engine control, in-car entertainment and communications, and many other functions. The key challenges facing the domain-specific systems on a chip program is to devise a complete tool chain to produce high-performance, flexible SoCs quickly and efficiently. That is, to identify useful accelerators to include and incorporate in the SoC and make them easier and quicker to design, produce, and program. This includes analyzing the source code of various application programs, identifying the accelerators that can be included to have the best impact on SoC performance, feeding this deep insight about the target domain into the SoC design process as well as the runtime environment, all in a highly automated manner so that SoCs become much quicker and easier to design, employ, and adapt to new requirements. The following video from one of our program performers, Collins Aerospace, includes a description of their approach to meeting the program goals and some demonstrations of the resulting technology as applied to their target domain of multifunctional radio frequency radar processing and communications.
The Kestrel Falcon is built for speed and agility with long, streamlined wings. They are small in size, but Kestrels are also fierce hunters. Like its namesake, the Kestrel program at Collins Aerospace is proving how domain-specific system-on-chip, or DSSoC technology, can pack a lot of performance into a small radio package to help mission-critical Department of Defense initiatives improve communications and situational awareness. The DSSoC, or Domain-Focused Advanced Software Reconfigurable Heterogeneous System-on-Chip, seeks to prove that there doesn't have to be a continued trade-off between efficiency, like that found in ASICs, and flexibility, the hallmark of general-purpose processors. This technology is led by Arizona State University in partnership with several other academic institutions. Collins Aerospace is applying DSSoC technology to real multifunction radio frequency, or MFRF, applications to deliver new and improved system capabilities faster than before while reducing power requirements. Radio systems are often measured with SWaP-C, which is size, weight, power, and cost. Each application of a radio system will have unique SWaP-C constraints, whether for installation in a Navy ship, on the wing of an aircraft, in the cockpit of an Air Force fighter jet, or on an Army surveillance UAV. These constraints can limit or inhibit advanced tactical data link, or ATDL, capabilities in Department of Defense platforms. Current radio systems have trade-offs between system flexibility, computational power efficiency, and implementation cost. Flexibility determines how easy it is to change processing tasks. Computational power efficiency measures the number of operations per second per watt. Implementation cost refers to the technical knowledge and time required to design a system. Current radio solutions utilize a combination of application-specific integrated circuits, or ASICs, field programmable gate arrays, or FPGAs, and scalar general-purpose processors. Kestrel evaluates the ability of the DSSoC to achieve ASIC-like computational power efficiencies, FPGA-like flexibility and performance, and scalar processor-like low cost of implementation. The DSSoC is composed of hardware and software technologies. The software technologies include ontological analysis and an intelligent scheduler. The hardware technologies include a collection of system processors, easy-to-program general-purpose ARM processors, ASIC kernel accelerators, and flexible domain-adaptive processors, or DAPs. The focus of Kestrel application programmers at Collins Aerospace is to quickly deliver new and improved capabilities to the warfighter and leverage DSSoC technologies to meet system performance. The Kestrel applications being deployed to the DSSoC include spectrum sensing, geolocation, and an ATDL. These three applications will be run simultaneously to demonstrate an MFRF system using the DSSoC.
We're in the lab to demonstrate our Acumen spectral sensing solution. We have two development boards that we're using to emulate the DSSoC system. We have a terminal up that is executing our spectrum sensing algorithm on the DSSoC running in a Linux environment. And you can see right now the intelligent scheduler is determining which processing resource on the DSSoC to utilize. Once our application reaches the end of execution, it will output 3 different spectrum plots for us to take a look at.
Our spectrum sensing application is detecting a frequency hopping waveform here. The top plot here is the power spectrum, and the middle plot here is the estimated signal to noise ratio of the signal that it's finding, and the bottom plot here is where in the spectrum it's finding that transmission. So the spectrum sensing application detected the occupied bandwidth, and now we're going to use the geolocation algorithm to geolocate that emitting source. In our scenario, we have 4 friendly sensing platforms and 1 enemy platform that we're trying to detect based on its spectral emissions.
So we have our 4 sensor platforms, and they're communicating pulse information with each other, which is used to generate a geolocation for the emitter. And if we zoom in on the emitter, it's hard to see, but we have an arrow ellipse right here that is our estimate for its location. The final application is the Advanced Tactical Data Link. The ATDL is the communication standard between friendly platforms. With the enhanced computational efficiency of the DSSoC, we'll be able to share larger amounts of situational awareness information between platforms. Examples include geolocation and the spectrum sensing, which we just demonstrated.
What does all this mean for the warfighter? Currently, our methods of communication are SWaP-C constrained. With the DSSoC, power will be reduced and processing capabilities will be increased. Previously, video transmissions were limited to larger platforms. Now, UAVs and other mobile end users will be able to transmit more data, so videos can be sharper and clearer in high resolution. Due to high processing requirements, geolocation data is not rapidly accessible to the warfighter. With Kestrel, detected communications can be used to geolocate enemy platforms and will become more commonplace. With lower SWaP-C requirements, these capabilities will translate to improved command and control in even the most disadvantaged environments. Kestrels are known for their ability to hover in midair, searching for their prey, and then swooping down to attack. The Collins Aerospace Kestrel team has shown this same patience and determination in demonstrating DSSoC technology. Over the past 3 years, they have worked closely with partners to develop and tune the technology for DoD MFRF application needs. To learn more, visit collinsaerospace.com.
So Collins Aerospace has shown us examples of the DSSoC accelerating advanced geolocation and communications applications. The DSSoC was designed in a few weeks rather than the years it would have taken before the DSSoC program. But multifunctional RF is just one example domain, and the DASH chip is just one example SoC. Future generations of powerful, efficient, and flexible SoCs applicable to many domains and designed in days will be possible thanks to the technologies developed under the Domain-Specific System-on-Chip program. Thank you.